Two of the most important applications of the relationship between electricity and magnetism are the electric motor and the electric generator. By definition, an electric generator is a device that converts mechanical energy into electrical energy using electromagnetic induction. The reverse conversion of electrical energy into mechanical energy is done by an electric motor.
This is a very simple and basic structure of an electric motor. We can see the battery, the commutator, the brushes, the copper wire loop, and the permanent magnet. The brushes are attached to a wooden support, and the commutator is fixed to the loop of copper wire. The commutator rotates freely, rubbing against the brushes. Now when we pass current through the circuit, this creates a magnetic field around the wire, which interacts with the field of the permanent magnet to produce a rotation of the loop that looks like this. The electric motor and the electric generator are related like two sides of a coin.
An electric motor is a machine that uses electric energy to produce motion. Electric motors operate a variety of devices, from vacuum cleaners in the home to windshield wipers in the automobile to conveyor belts in the factory. All electric motors that produce rotation work in essentially the same way as a direct current series motor, which is commonly used to drive electric railroad cars. Current flows through a wire to a block of graphite called a brush. The brush transmits current to the commutator, which consists of two or more semicircular split rings. The commutator is connected to a large coil of wire called the armature and to the output shaft. Current flows from the commutator through the armature, then back to the commutator. Current then flows through another brush to one or more electromagnets, each made up of a wire coil wrapped around a piece of iron. This flow of current through the magnet's coil produces a field of magnetism. The field has a north pole and a south pole, as shown in this simplified picture. The current in the armature, one loop of which is shown, interacts with the magnetic field in the coil, producing motion. The direction of this motion depends upon the directions of the field and the current. The split ring of the commutator interacts with the brush to keep the armature current flowing in the same direction relative to the field. Thus the loop and the output shaft continue to rotate in the same direction.
Hi, welcome to Holyfield Physics TV. Today we're going to look at the magnetic effect on electric currents, and this is part of the OCR Physics A2 course, Fields, Particles and Frontiers of Physics. It's the direction of the field and the current and the force experienced are all perpendicular to each other. And to figure out which is which, we use Fleming's left-hand rule. So we have our thumb, first finger and middle finger all at right angles. First finger is the field, second finger is the direction of the current, and the thumb is the direction of motion of the conductor. As you can see, all at right angles to each other. It's like an XYZ graph. Now if we have a nice uniform magnetic field flowing left to right on the screen, it means the north pole is on the left and the south pole is on the right. So we've got our field to the right. Into that field we put a conductor, pass a current through the conductor, current value I, so the current is into the board, into the screen, and that gives us, with Fleming's left-hand rule, a downward motion, a downward force. If we have alternating current, we get the conductor to oscillate, depending on the frequency of the AC. Current flows backwards and forwards, so the force is up, then down, then up, then down. If we have the right conditions, we can set up a standing wave. So there's the fundamental mode of our standing wave. And the factors that are going to affect that are the frequency, strength of the field, the flux density, and the mass stroke tension of the conductor. So it's the mass per unit length, and also possibly the tension, the weight that we have hanging on the conductor. And as our B field is to the right, pass a current through that B field. This one's coming out of the board, out of the screen, and we get an anti-clockwise field using the right hand thumb rule. These two fields combine, and this is what causes the force. And so the effect we have is that the field is stronger under the wire. This gives us the force upwards. Now, to look at the size of the force, it's going to be proportional to the two fields that are just combined with each other. And those two things are to do with the flux density and the size of the current. But the other important thing is the length of the conductor that's in the field. And we get the magnetic force FB equals BIL. F equals Bill. But left hand's rule, everything's got to be perpendicular. So we need to put a sine theta into this. So our final equation is F equals BIL sine theta.
In a pressurized water reactor, water is enclosed in 3 separate but interacting loops. In loop 1, water becomes intensely hot as it absorbs heat from the energy of nuclear fission. But because it is under very high pressure, the water doesn't boil and remains a liquid. Pipes from loop 1 wind through a steam generator tank that is part of a second, lower pressure water loop. Heat from loop 1 boils the water in the steam generator, and the energy from the steam powers turbines that drive electricity generators. The steam is then cooled and condensed in a heat exchange with a third water loop, which carries water from the cooling tower. The liquid water in loop 2 then returns to the steam generator where it is reheated and the cycle continues.